All right, so let's talk a little bit about the dot product and what that is. The dot product is a way to analyze and output a scalar value, meaning a single value that correlates to how two vectors align. Okay, so that's kind of a complicated way of saying we're just going to look at two directions and see how parallel or perpendicular or opposite those things are. And it's going to give us a number based on that. And that number falls between -1 and 1. So in this picture here, so say the vector we want to analyze against to see how closely they align. So I've got this picture here, and I've got this red vector and this blue vector here. Let's say the blue is the vector we want to see how close our red aligns to. Well, right now, our red vector is perpendicular to our blue. So in that case, it will return a value of 0. If we were to rotate this to be vertical, because these two vectors align perfectly, it would return 1. If this red vector were negative or pointing the opposite, it would return -1. Obviously, this way it'd also be 0. So here would be 45 degrees would be 0.5. And it doesn't matter. This vector can be anywhere. It doesn't care spatially where it is when it's doing that analysis. It just looks at the orientation of the vector, the two vectors, and says, okay, this is how they relate to each other. So it's a really useful thing. The first time I actually ever came across this was one of the first places I worked. It was how to emit particles only behind a sphere that was traveling the sphere was traveling in a specific direction, and I just wanted to emit particles from the back of it. So we looked at the dot product and said, okay, so say if this circle were traveling up, anything that had a threshold between 0 and -1 emit particles, and anything above wouldn't. So anyways, you can use it to analyze those sorts of things. All right, so with that said, I'd like to do the same, because when we talked about, okay, what are some comparisons that we have, we were kind of looking at most of these faces are perpendicular to the direction of the rain, i.e. the negative y-axis. So let's go ahead and create an attribute wrangle again. And before we start typing code, let's think about the two vectors we want to analyze. Okay, we're going to give it the rain direction, similar to what we did on our VDB potential flow. We're going to give it this -1. So let's go ahead and write that. Vector dir, or direction. And let's actually, we can create a parameter just so you guys can try a few different things. So we've got that. And I'm using CHV. The V creates a vector parameter. The default usually just creates a float. Now, what's the other vector we want to compare against? And I know you clever kids out there are going to be like, oh, well, we can look at the normal. Well, yes, but we may also get into trouble because this is a pretty detailed sort of surface. We might be getting some other faces in there that we don't really want. So we can actually, from our shrink wrap, we can create a normal off of this and use that as the direction. And we can actually create a VDB from polygons. Oh, let's just do 0, 2 again. And let's feed this guy into the second input. And what I want to do is similar to what we did up here where we're sampling our volume. I want to do the exact same down here. Now I know you could copy and paste, but we're here to learn. So we're going to create a vector. and we'll call it grad. And we're going to do a volume sample, but it's a different type. We're going to sample the gradient, volume gradient. And it accepts the same sort of arguments that the volume sample does. We need the volume which we want to sample, which is 1. And the primitive is 0, and we want to sample at the location of our point positions. So we've got 2 vectors now, our direction and grad, which we can compare against. But let me just talk briefly about our gradient. So what is the gradient? Well, I mentioned before, let's pull up our whiteboard. So say we have our object here, right? And we turn this our object into a VDB. Well, that SDF that is being created is storing the distance the voxel is from the surface. So we'll just say this voxel, we'll just say this box is -1. This voxel here is -2. This voxel here is -3, and so on. Now this one here will be 1. This will be 2. And this will be 3. That's a 3. Interior values are always negative. Exterior values are always positive. And that's how it knows whether or not a particle or a point or whatever, if it's inside or outside. And that's how a lot of collisions are figured out. It says, whoa, you're inside. It's a negative number now. We got to get you out. Well, and how does it get it out? Or how does it say, hold on a second, you do not belong in here, for example, in particle collisions? Well, it computes what's called the gradient. Now, the gradient is analyzing, so it looks at the voxel, which say is -3. It looks at all the surrounding voxels here and says, okay, what is the direction that values are increasing? And therefore, in this case, -3, -2, -1. The direction is going to be pointing towards the surface. That is called the gradient. Okay, so it's analyzing this scalar field and returning the gradient. And so that's what we're doing here. We're grabbing that. And if you were to do, just to visualize a bit better than what I could draw, we do a VDB analysis on this. And here we go, operator, gradient, scalar to vector. And we have our visualization guy here. All right, sure enough, you can see all these vectors are pointing outwards. And as we shift, you can see they're all pointing out. All right. So we're going to use that now to feed into our dot product. All right. Now remember, the dot product returns a float between -1 and 1. So let's do a float dot equals dot. And you can see the 2 inputs. It expects 2 vectors. All right, so we've got our dir and grad. Now, here's something that's really important when you're doing something like the dot product. It's always important to normalize our vector, which basically means it gives the vector a length of 1. Because a lot of times in effects, especially with velocities and things like that, all these vectors have a magnitude that can be much bigger than 1, smaller than 1, everything else. And these computations, whether it's dot products, cross products, etc., it's all doing multiplication. So it's important to just make sure we're always comparing apples to apples, so to speak. So we're going to normalize that. And assuming the user is just going to give a value between, -1 and 1, but it's always good just to make sure, even if they give a -2 or -10, it'll still output what we're expecting. All right, so let's take a look at just visualize what dot is returning. It's not going to return anything useful because we have not actually defined our direction. So let's go ahead and push this button to expose our parameter. And if we just set this to 1, all right. So all the values that are pointing, or all the faces that are pointing straight up are getting this white color. And everything else, it's really tough to tell because, again, remember, this goes between -1 and 1. If we were to set this to -1, you would see we're getting all the underside faces. And just to confirm that this is behaving, we can see, okay, the color value is -1, and there's a lot of zeros and so on. Something though that's interesting that I did forgot to mention is, okay, all these zeros, right? We already know, like, okay, there's not that many faces that are perfectly perpendicular. No face is rarely perfectly perpendicular. There should at least be some kind of value in there. And the reason for that is on our VDB from Polygon, well, VDBs do this thing to make it really efficient, is only create voxels where it thinks it's going to be necessary. And it uses these exterior interior bands, which means we'll populate the distance value 3 voxels from the surface on the interior, as well as 3 voxels from the surface on the exterior. And then everything else we're just not even going to bother computing. So you can obviously crank these up, but an option that we want is fill interior, which means it's going to populate all the voxels that are inside this geometry we're creating the VDB from. And you can also look, if you middle mouse on the VDB from Poly, okay, we're at almost 2 million voxels here. If I uncheck this, it's going to be significantly less, 671,000 voxels. So, it is important for resource management and stuff to keep that in mind, but those are pretty low numbers, so we're fine. All right, so now that we have that, we can see, okay, there's more. All these now are changing color. You can see that difference. So we can see now we have healthy values ranging between -1 and 1. All right. That's all well and good. Let's set this back to 1. So it's all the top faces. That's great. But we really don't want the faces that are pointing straight up that are aligned. So we could put the direction to be an X, but that I don't think is really going to give us what we want because we have faces pointing both on the X and Z axis. So remember how I said quickly that up here on the fit, we could remap this. Right now it's just doing a linear interpolation. Well, let's go ahead and fit this first, this dot value. So let's create a new float. And we're actually going to control that with a ramp. So first let's fit 1, 1, our dot, to be between 0 and 1. All right, so what is fit 1, 1? Fit 1, 1, so maybe you guys are familiar with, there's a helpful expression called fit 0, 1, which it assumes the input falls between 0 and 1, and then you're just specifying the new min and new max out here. There's also one called fit 1, 1, which is assuming this input, this first argument, falls between -1 and 1, which our dot product does, and then we're just mapping it to be between 0 and 1. Now that we have this between 0 and 1, we can create a ramp. Ramp equals ch ramp. So ch ramp needs the name of the ramp, so we're just going to call it, I don't know, dot ramp. That's entirely up to you. And then the value we're going to remap with this ramp is called ramp. It's going to be this 0 to 1 range. The ramp, the ch ramp, always requires, I don't know if it's a requirement, but let's just say it's a requirement, needs to have values between 0 and 1. That's why I did that up there. Okay. That, and now let's actually change our color to ramp. Oh, it's not creating. Oh, you know what I think it is? Okay. I don't think you're allowed to actually put a space in between there. Let's call it dot ramp. Sure. Yeah. Okay. Generally, and I should know better. You never really want to be using spaces anywhere. All right. Yeah, there we go. Okay. All right. So this is our 0 to 1 ramp now. If I were to say pull this middle area up, this down area, and we can say put this at 0.5. All right, we are now isolating. We're no longer really getting the top faces. All right, we got some of this stuff behind here, but that's fine. But we're only really getting the side faces. So this is exactly what we want. But we also really like this distribution where we're just getting it on these ends and we've got some nice, kind of variation in there and whatnot. So what we can do is we've got this color, we've got that color before us. Instead of doing CD equals ramp, which just stomps on whatever color is being fed in, let's do CD times equals ramp. And there we go. All right. So now I think we're pretty good. The only thing is we have it on the back side here. We don't really want to be emitting, but when we look through our camera, we don't see it. So I think we're ready to start sourcing our particles and creating these drips. But keeping in mind that we are simulating and we always want to try to keep our simulations efficient, let's just go ahead and chop off all of that stuff back there. And an easy way to do that is just use a clip sop. And let's set the direction on the z-axis. And then let's just pull this back to around there. Just want to make sure. Yeah, good. Okay. All right. So in the next video, we'll actually start getting in the business of simulating.